stroller, but my son a couple of months ago took it for one of his toys, and so now it's in the home of my parents, and so I have to go manually this way. Okay, so let me start by a very brief description of what are the Euler and the Navier-Stokes equations. Okay, so these are two systems of describe the motion of an incompressible fluid. Okay, under very idealized assumptions. So all the fluid is assumed to be incompressible, and then if you assume there is an absence of friction between nearby fluid particles, then you have the Euler equations. If you assume that the friction is present and it's ideal, that's with respect to the then so in both systems there are. So the first one and the second one is the velocity is a function of time and space, and velocity, the speed of the fluid and time t. Okay, it's a bit more complicated to describe, so it's actually a scalar, and its gradient is a force, and you have to the fact that the movement might try for the part the fluid occupies, but since the fluid is incompressible, it's going to react. So this force, which is understood as measures of the constraint of incompressibility. Okay, so here are that there is the time, there is this nonlinear term, which we write down as the divergence of the matrix V tensor V plus the gradient of the pressure equal to a constant, which is nu times the Laplacian of V. And then there is the incompressibility constraint, which is that the divergence of the vector field V is equal to 0. So if nu is bigger than 0, then we have the Navier-Stokes equations. So there is friction. And if nu is equal to 0, then we have the Euler equation. Okay, so usually the advectives, this term over here, is written in another way. So if you write it component-wise, derivative in a vi, so this is a vector and this is the I. But usually if you look at it, you will see it written in the following way. And the reason of this guy, this thing over here, but since Vj is divergence free, of course, write it in the following way. Okay, so and is the usual Laplacian, which is simply the trace of the second derivative vector field V. Okay, we are mostly going to think about in a fluid which is occupied, which might be the three-dimensional solution sometimes. So they would be defined as three-dimensional or two-dimensional. Interval, a time interval, or an infinite. This is called the Cauchy problem, and then we at some distribution V0. Talk even about ancient solutions, that is solution forever in the future. Okay, now these are it's an enormous amount of equations were derived actually more than 200, and the equation is attributed to the correct person who derived it first. The Navier-Stokes equation. There are difficult open problems. The most famous is the so-called blow-up problem for the three-dimensional data. You know it exists for a finite amount of time. Time existence depends on how long in some smooth. And the problem, which is long, the millennium problems, is whether we assume infinite time or not. So now this touch this issue actually, and I don't know about the relation about and if there were a relation, probably unlikely. Okay, so because we're okay, so we start with a very simple solution. If you have a smooth solution, I'll multiply with some computations, and you will find this which I've written over there. The modulus of v squared divided by 2. Okay, so the fluid is actually incompressible. I should have told you it is constant. Okay, so if we normalize the constant equal, then this quantity over here, I mean, it's just essentially rate of change of the density of the kinetic energy of the fluid. You see in the red term, actually here, so if you insist that the solution, the computation is really obvious, it's less obvious for Navier-Stokes. You need, but I mean, it's not too complicated. Now, if you integrate in the whole, if you take the periodic situation somehow is decaying fast enough at infinity, then this blue term, which is a divergence, even the Laplacian disappears by integration. And here, which gives you the total kinetic in terms of the viscosity. You see something interesting so if nu is that a classical, it's no surprise because there is no external force, so essentially there's your energy, your mechanical. Okay, so now let me talk about weak solution equation. So in the literature of partial differential equation, it comes often that you treat the system of partial differential equations in some occasions by considering weak solutions. So this is sometimes subject to criticism by people who are not working in PDEs. There are a lot of reasons actually for considering generalized solutions. It's quite natural from the point of view of physics, because there are physical problems in which the solutions actually, they're not smooth. I mean, they might have singularities. That Generalized solutions of the Euler equations were much earlier by physicists than mathematicians. To define generalized three ways of defining equivalent. So if you go back to the equation, which in the case of Euler I'm going to write down over here. Okay, you see that your takes always in a linear way. The only so you need to define what is the product. And if you have an L2 function V, and then you can take derivatives in the sense of distributions, and you have a well-defined distribution. So part of the system is the divergent range. This is completely linear, so V in L2. So that's one possibility. Another possibility, which is the following. So take each time, and if you get, you write equations which are varying in time, the Fourier modes, periodic situation. Now, in this situation, the PDE becomes a system of ordinary for AK, right? So when you find the time derivatives of, but when you take the Fourier series, we turn algebraic expression. What happens is that the time of each AK, okay, complicated expression, not so actually, okay, so you find a series essentially. So the form, the time derivative is equal to a certain series. Now, if you want to know when the series is converging, the least you need to make that sense is that the square of the Fourier coefficients is finite. Of course, here you recognize that this condition is little L2 in Fourier, which means actually that you just need that the velocity at each time t is in L2. Okay, and then you have a well-defined system of ODEs. Now let me though introduce you to another way of thinking about generalized solutions. This is very natural, and if you open any physics book, you will realize that this is what continuum physics is doing when deriving the system of PDEs. Okay, so what you could say is that there is the fluid which is sitting, okay, and then there is the velocity distribution. Total amount constant because the fluid is incompressible. That the amount of fluid and the amount of fluid particles which are equal to 0. So this boundary integral is equal to 0. Okay. Then you have as many particles acting, as many total amount of mass in that fluid element is constant. Now you can do something similar. So of the momentum, so the total momentum is the integral over this omega. The momentum is changing for phase and instantaneously, and they are carrying their own momentum. Okay, so this is this boundary. And then you have a force which is acting on the boundary. Okay, and that force is actually this boundary integral multiplied by the normal. Okay, now if you look at, they make sense of this integral, right? So if you have a P is the same P, yes. So if you look at these equations, right, so they make perfectly good sense if, for instance, the velocity and the pressure are continuous. Right? They make perfectly good sense. Now,
but P is only up to a constant.
Sorry?
You find only up to a constant.
Because the of the unit normal is equal to 0. Right? As this integral. So nu is no. So now, this is what, say, if you open lambda, you out of the fluid. And then, of course, if you turn it up, but wait a second. So, it's actually the integral over omega of the divergence, right? And now, if you know that this identity is true for every fluid element omega, then of course this integral is true. This integral identity is true for every fluid element omega, and this means that the divergence is vanished, right? Say very well, the basic law of physics are actually the ones which I've written for every fluid element. And they make perfectly good sense if they are written in this form. So even if the velocity and the pressure are just continuous, right? So you could say it makes perfectly good sense to define a solution just to have a distribution of velocities and continuous functions. And these integral identities, they be satisfy good bounded open set omega. It's an easy exercise, all the but you see that in some sense, you could even argue that this concept of solution comes even before the one which I've given you in form, right? So the one in differential form, they're actually derived by the one in integral form that you have here. So you could even argue that these are fundamental than the arguments. So this is just the starting of the surprise in 1993, and which would be a solution in all of these three senses, because they are perfectly equivalent. Solutions which are compactly supported in time and space, but which are trivial. Okay, solutions, and this would mean at time t equal minus 10, the solution is identically 0, and then it becomes 0 again later on. Okay, so it's pretty surprising. You would solve any problem about without getting energy for it. These energy, in particular, they would be creating energy for free. So they would be equal to 0 at some, but then they would have positive kinetic energy at a certain later time. Okay? So in particular, they violate the identity a few slides ago, that is integral, for instance, on the periodic term. And the reason for this violation I'm considering are not solutions which I told you on the identity of the. So in particular, these solutions are not for the Euler equations. So now, there was a difference which was given in 1998. It's obvious that these solutions do not. Anyway, if you plot the energy of these solutions over, because the functions are only L2 of time and even find anything like so it's a complicated construction of Schneiderman to show that there are so kinetic energy has a nice profile and it's okay. So we will see that these were very constructions and with DD. So this is the first time that I'm. And so I give it, but any time that it means, so in 2007 we actually supported solutions which are only in L2, the velocity is always fine. This answered floating around in the literature because this Scheffer and in particular, not only the kinetic energy is increasing somewhere, so they are violating the total constant, but the kinetic energy could even be plus. Okay. Here's the question whether this kind of triggered by the fact that the kinetic energy was showed that the kind of behavior in the energy space. Not only that, actually ask whether, of course, rating the uniqueness of solutions. Because so of course you could say, okay, and one way I could say I don't want. Let us consider the kinetic energy, for instance, is going down. The initial value equal to 0, then the kinetic energy has all uniqueness. Which is proved by these methods that essentially none of the criteria which have uniqueness of weak solution. If kinetic energy has to go down, sure, from the initial data equal to 0, you get unique from this condition. But if you start from a sufficiently wild initial data for a sufficient use initial data, then there are energy which is decaying down. Only that, in fact, does not have to be so discontinuous in first construction, and this is a risk. Okay, now this was picked up in the video of people, and it has been showed several equations. Because the techniques that we are using can be exported in several situations. So it's a behavior which is which you can see much more often for weak solutions of several evolution equations than one would initially imagine. And here you see a just non-exhaustive list of people who have been working on this.
So there's nothing similar to entropy.
Yes, something similar to entropy condition, but fails to give you uniqueness. Saying that it's situations, so indeed by this former PhD student show that even for system of concepts, an entropy condition alone in more than one space dimension is not enough for giving uniqueness. So it's a quite subtle if you want to give uniqueness of these one entropy condition. And now what was actually more important, not only this proof than Scheffer and Schneiderman, but this theorem into a framework. So before the construction of which was didn't look like any other construction which was present. So what we pointed out in 2007 is that not only you can prove this theorem, but you can prove it in a way which is very well understood in the literature, and it's used in several other situations. It was never used in equations of mathematical physics of this type, in this type of evolution equations, but it was a very well developed theory which provided a lot of monster in differential. So let me give you a couple of examples. Type of problem in which you have, so this is called, you have a PDE of the following type, if you want. So you have a set of matrices, and you are looking at functions U, so maps U, whose derivatives take values in this set of matrices. Okay? So this is very general. So this is called a differential inclusion. Of course, depending on the day, you might find very differential equations, right? So you might find equations or very no-rigid situations. To some rigidity, and then people consider not C1 solutions, which would be kind of from the point of view of having one derivative, but Lipschitz solutions. In that case, you only have differentiability almost everywhere, good as being solved omega. Let me give you a very, very elegant problem of this type. You will not have much time to solve it, so I will solve it for you, or maybe you're quick enough to solve it. Two values. So K consists of one matrix A, we are in 2 by 2. Okay? There is a vector valued map which is taking values A and B. So the gradient has to be discontinuous, right? So you could imagine that the gradient is necessary and sufficient conditions of such a map. And you see, you will have an A and then a fine function with B over there, but they have to agree on the boundary. Exercise to see that the necessary condition of the existence of a non-using the gradient is that, so the direction of, so this gives you that, the vector directing the lines of A and B. Okay? If A minus B is, then you take one element, well, the unique element is 2 by 2, the matrix, which is having slope A over here and slope B over here, and, okay? So a roof type. Okay, and T Bern-Kirchheim, both fact. So you can find 5 matrices, A1, 5, okay? The rank of, right? So the difference matrices is always going to be. On the other hand, of u is taking values on all, but gradient of u is not a fine, or at least is values. Okay, so it must be a very complicated, right? So it's not a map with continuity. Then the difference between the two values of the gradient is one map, right? Action consists of essentially affine pieces. So it's very hard to imagine, and because 5 is optimal, it's proved by Bernd, and that if you try to do this. So then you would have a rigidity situation. So if you have matrices whose difference and a map whose gradient is taking values on these 4 matrices, then the map has to be linear. So it takes only one value. Okay, but let me give you so this is another famous result by Müller and Schwer in 1999. So there are systems of partial differential equations, elliptic, which are Lipschitz and nowhere differentiable. Elliptic equations or do not have an interior. So now, of course, you could wonder, how does this relate to differential?
Well, we use these Lipschitz and nowhere differentiable.
Right. And they are solutions to elliptic systems. Systems, not equations. Systems. So more than one unknown. Okay? So of course you could ask how that is possible. Well, think about it. If you take the Cauchy-Riemann equations, right? So the Cauchy-Riemann equations are a typical differential inclusion in that term, right? So what does it mean? It means to be conformal. It means that the derivative belongs to the set of, that is, the derivative multiple of, right? A special orthogonal matrix, positive matrix. Now, of course, if you have, which is Lipschitz, then it is holomorphic, right? So this theorem is expressing that elliptic systems, and the nonlinearity is there. All of this actually, so for instance, these 2 examples on fork, which is very old in differential inclusions, as the 35 years old at least, so not very old. 2 instances. And 2007 is that you can recast the Scheffer-Riemann theorem. You can prove it by prove both the result of Kirchheim and the result of Müller area. Bernd's result is that because I find it fundamental for those in 1999, they discovered a very surprising connection. Just a very basic example of a type of constructions work, right? Toy problem, and I'm going to show a very irregular PDE simple, okay? So the PDE is this diagonal equation in which I'm for is equal condition. So I want to produce a bad solution of this PDE. What I'm going to do is I'm going to do the PDE, it solves an inequality. Okay? And then I set up an iteration scheme, and at each step of the scheme, I'm producing a new map. So now, along the road, so while I'm setting up the iteration, the gradient is always going to have modulus less than 1, but in an integral sense, the distance solution, this beta is less than 1. So if you have such this integral exponentially fast, okay? And so the modulus of the gradient in L1. Now, that does not mean that the functions phi converging, right? Have that the modulus of the gradient is converged, but the gradient in L1, that is perfectly possible, right? So you might have, for instance, something which oscillates a lot. So now, there's one thing which I'm not going to show you, which the theory does for you in a sense. So if you construct this approximation in the way I'm telling you, there will be actually strong converged gradients in L1. And so I will have produced a solution. So this is what differential inclusions does going to touch. To construct phi plus 1. Here is an iterative. Your function phi k, I will use phi k plus 1, and along the iteration. Okay, so what I'm going to do, I want from this guy. So now, gradient phi, very tiny. I can assume that gradient of phi is constant. It's almost constant. Very, very small. The gradient will tell me I'm almost a, okay? So assume for the moment that you are a phi. So right? So you have this condition. So now the question is, you have slope less than, construct a perturbation which will have, so of course, if this is something like this, right? So you can do a zigzag. And if you do the zigzag very fast, you will stay very close to your initial function, okay? Now, I told you that I want the new function to be smooth, so I will not do a zigzag, right? So I will do a smoothing of the zigzag, right? But of course, if I do a smoothing, most of the time, in an integral sense, the slope will be very close to 1. Okay, now there is a problem though. You see, in this region, right, in this region, the slope is this way. But in here, the slope might be, so in this region I want, but in this region, exactly like that. So what out of my perturbation is I will take a function c, which is small region of the region. And then I map my perturbation, which is the cutoff. Of course, the cutoff is a very high gradient, right? So I insist the function to be 1 on a very large. You see that the following happens. So when I do the oscillation, when I differentiate here, the lambda pops out and this lambda. When I differentiate the cutoff, it is 1 over lambda. So you see, without the constant c, I wouldn't have the perturbation, which is good, which improves. Now, gets this 1 over lambda. So very, very fast. So if I'm making a very, very highly oscillatory, kills, okay? In particular, if my perturbation is pushing, and if I take care of oscillation, I'm still enforced of the gradient is less than 1, okay? So I've done this locally, and I'm adding perturbations on not every, okay, because I only have the slope, which I want to improve, this one in particular. So of our theorem in lot of Kirchheim's construction, Schmüller-Schwerak, and all have been working on this. This kind of naive method actually can be applied in a lot of situations, and it gives you and the bad behavior is you are piling up a lot of oscillations on top of each other, right? So each time that you go one step in the iteration, you're adding very fine oscillations, very fine wigglings, okay? Now, there is, however, an important point, and that is the Müller and Schwerak paper is actually a landmark result because they noticed in 1999 the following. So, what analysts were doing in the literature of differential inclusions, differential geometers were doing already since the 50s in differential geometric problems, although they were using a different language for it. So what they showed is that there is a connection to what is called nowadays the H principle. Barella concept introduced a series of paradoxical differential geometry, and one of them you there. So the Nash-Kuiper theorem, the construction in geometry. To tell you exactly what is the H principle, just going to tell you what is probably the mother of the H principle. So the Nash C1 isometric embedding theorem. So you can think about this as the mother of Gromov's theory in a sense. In fact, most of the H principle constructions are inspired by Nash initial result on the C1 isometric embeddings. Okay, so now what is an isometric embedding? So you have a Riemannian manifold MG, and you are looking at maps which are going into the Euclidean space, for which these maps are an isometric embedding. So what does it mean? Isometric in principle is that if you have a curve and you look at the image of this curve, they have the same length, right? So and with the metric, and base you measure it with the metric. In what follows, there is a corollary to state the theorem. I read the corollary. So the corollary of this theorem by Nash, actually by an improvement of Kuiper, of Nash result, which I'm going to tell you. If you take, you can actually isometrically embed it in dimensional space. So you have really the standard sphere, which is as big as a normal sphere when you do isometric embedding, which is good. But you can actually manage to, in a C1 way, all ball. Okay? You can do that not only sphere, you can do it even, so you can do a piece of paper, 1 meter times 1 meter. So you have to have a piece of paper 1 times 1 meter inside a very small region. Why it is quite striking, this thing? First of all, not C1 is, so if it were a C2 isometric embedding, so C2 isosphere in the three-dimensional space have to be unit balls, right? So you wouldn't be able to crumple everything in small space. Okay, but on the other hand, yep. So you probably, so this is a flat space, right? Problem isometrically embedding it into space, you face it always, right? So you would like, or in your wallet, right? So what you do, of course, you fold it, something like this. But this is discontinuous, right? So, and this is easy anyway. Nash could do that C1, the piece of paper in the pocket, without points, okay? Well, at least not in practice. So that is what the theorem says, and why the Kuiper theorem is actually much more general.
Those maps, can you compute it by using a computer?
Yeah, wait, it's not actually numerical simulations yet. But you see, so it's elongated the one you, and what you can, if you compute things carefully, you can maybe follow, I think, iteration, which is not very large. I mean, follow 5 or 6. See some of the wrinkles, but it has been done very recently by people in numerics in the last few years. Oh yeah, I can show a lot of pictures actually on the. Actually, what the following. So if you take a short embedding, and a short actually reduces the length of curves. So for instance, to a small sphere, then that is a short embedding. Nearby any short embedding, uniformly close, there is always a C1 isometric embedding. Okay? Here, this construction which I gave you for the essentially what I showed you for the iconal equation is that if you have a solution for which the slope is less nearby, that will be an actual solution of the PDE is equal to 1. And that, of course, is very the zigzag. But here, those ones will be C1, and you cannot take the zigzag, so it's more tricky. Okay, so if you take 2007, actually, it comes with an H principle. So it tells you sub-solution, an interpreted solution, 0 would be a sub-solution, for instance. Nearby, they're interpreted in sense. And one of the big caveats in this business is that up to now, people in differential geometry type space, so you have a C0 function or a C1 function, differentiable with the. But people in differential inclusions worked with L-infinity spaces. So, in Euler, a Lipschitz solution, in which you have a function which is differential but not completely bounded. So I say actually so far that you're going to see that there are actually C0 type constructions even theory of differential inclusions. So now let me switch. Let me tell you we care about weak solutions. Well, probably we shouldn't, but you very roughly is called. So you remember the energy identity, right? So here is Navier-Stokes epsilon, and here is the balance law for the energy. So the time derivative of the energy is equals epsilon. Now, one of the most dynamics is the Kolmogorov theory, fully the so-called K1 theory. The theory predicts that it seems that the state in front, in fact, in a statistical sense, so in a way, this total is a fixed proportional amount of these. Okay? And this beta over here is a constant, right? In particular, if you let epsilon, dissipation term will survive because beta is in of epsilon. And so if that is true, often is the regular solutions to now the Navier-Stokes equation for epsilon going to not a smooth solution of the smooth solution preserves the kinetic energy. Okay? Now this is very interesting. There are some assumptions for instance, that you are looking at a macroscopic scale of the fluid. Let us keep that. Now, although this is what the theory predicts, of a sequence of solutions to this dissipation is bounded away from 0, independent of. So the theory tells you that this behavior, and what I am claiming is that if you look into the literature example, okay, in a very famous paper in 1940, the 20th century physics, he was solving the Ising model in 2D, for instance. So he said, we could, in fact, put epsilon equal to 0's theory. He discovered Kolmogorov's theory independently from Kolmogorov, although this was done by Kolmogorov 8 years before, so he didn't know the paper. He was told after. And you could develop a theory of ideal turbulence. And in doing so, in this famous short, he actually wrote down a mathematical conjecture, which is very precise. So his conjecture was the following. So if you take a periodic solution of the Euler equations, and if they satisfy a continuity condition of this type, so it's a Hölder continuity for this exponent is bigger than 1, then the total kinetic energy is constant. And if you remember what the total kinetic energy is C1, and if you are C1, this condition would be 1. Okay? So it's this threshold 1/3 is actually borderline, meaning that if you take alpha 3, they're actually solutions which dissipate the total kinetic energy.
It's a 2D of ED.
3. So now, of course, Onsager is reachable, and you might wonder whether I'm cheating you. I'm saying just a story because, often mathematicians stay and they give their own interpretation of it, or whether Onsager is precisely stating truly remarkable and perfectly sound from the mathematical point of view, without any imprecision. What he's really stating is, and it's actually a weak solution for him, since he's not used in 1914 and he's not a mathematician. So he's expanding the solution Fourier series in the periodic, and he's taking the definition of which I told true Fourier series, equivalent to the theory of distributions, actually, by simple exercise. And he's truly saying so. So it's quite interesting because he states the conjecture and then he has a paragraph. Of course, I should tell you a solution which is not differentiable. And you could take several definitions, but through Fourier. He doesn't mention what are the other possibilities, but he says it's just one possibility. Okay, so actually this conjecture was proved by Eink, a student of Onsager, and Constantin A. and Titi in 1993 for what concerns the conservation part, so the first part of the conjecture. And there are several works in the literature which have refined that. Now, if you look at part B, of course, you could wonder when is the first time that it was mathematically proved in a rigorous way that there is a solution which is not conserving the energy. And that proof was given by Scheffer in 1993. Doing that, though. I mean, he didn't know about the Onsager. So, what is actually the picture of Onsager? A very quick hint. He takes the Fourier coefficient and it just says, okay, this solves an infinite system of ODEs, and what you can expect the system behaves way if you have a random solution. And if it behaves in a chaotic, what you could do, you could look at numbers which are broken in dyadic. And typically, only modes by shells should be important in the nonlinearity, right? So if you're looking at modes which are from shells apart, essentially their interaction shouldn't come too much in the equation. So that's one assumption. And if you look at the total energy, you look at which kind of satisfied, the only law which makes sense in physics, because it would be the only scaling law invariant which is independent of the systems of measurements that we have, so and of the fact that we are in time in seconds, it would be this law over here, which is actually the Kolmogorov's 5/3 law. Now, one important caveat is the following. So when you're looking, all of these considerations should be done when the viscosity is present. So what this consideration tells you is that, okay, so this decay is correct. The wave number or the inverse length is comparable to length, the inverse of the frequency is comparable to the, and at a certain point important, and actually the dissipation goes much faster. And that's kind of the tail of the dissipation. But in principle, the viscosity, if it's not there, if it were equal to 0, then this value along all scales. Okay? So the case of Euler for Onsager is clearly a mathematical speculation, right? So this idealized this mathematical experiment. Now, of course, it's just it's difficult to tell from the point of view of data is a conjecture. He says so. Of course, you have continuous dissipative solution. It took us quite. Of course, what was the following point? If you metric embedding, right, it's very easy to show that there are curves which satisfy the H principle of the embedding of Lipschitz, but the G of Nash was C1 solution. So what we hoped is that you could update our bounded solution to acquire quite some work. I mean, it's absolutely not obvious, but it is 2011. So there are dissipative solutions which are, and in fact, let me tell you two interesting. I mean, this was probably the time in the literature in which you see a theorem which looks more like a differential geometry, right? So in which we are not category, but really in a C0 category. Now, if you compare at a technical level with graph integration, so convex integration techniques in geometry, typically it's a very simple operator, like the derivative along one direction. And actually what we're doing is we're really integrating the Laplaces, actually the bi-Laplacian even. So something like that was by Gromov relations. The conjecture is actually about Hölder solutions, and what we know, I'm going to tell you in a second, is that between bounded and continuous, then you would get, but we imagine very small, and instead, 1 year after, well, less than 1 year, prove that there are dissipative, and in our first theorem was this. Okay, and I mean, there are further work by a few people, which the theorem of other equations to different settings. In fact, very recently, Philizet and Vladvikol, that these constructions, which at the beginning they're very peculiar of the Euler equation, peculiar equations that 2007 paper, actually they can be generalized in several situations. In particular, it's being generalized to called active scalar equations, a very large class of equations. But of course, the biggest focus for us was this conjecture of Onsager, and our 1/10 exponent was improved almost immediately by Phil Izet in his PhD to 1/5. So you see that it's actually start getting pretty close to this 1/3. And well, so this was in 2012 his PhD thesis. It's a rather complicated, 200 pages, and together with him, we actually could simplify. I mean, a normal paper in mathematics, let's say, some 40 pages or something like that. But of course, you still find a big gap between 1/5 and the PhD student of Laszlo, Tristan Bukin, he actually observed that you can make your velocity almost 1/3 for almost everything. Okay? So now, if you go back to Onsager's conjecture, you will notice the following thing. This Hölder condition is not in time. It's only in space. But this constant is independent of the time. Okay? So, these solutions here, they are Hölder continuous in time and space. So they have a much stronger condition. Okay, so this is actually the current state of the art, so it dates back to 2014. In fact, what you can do is you can have all the correct exponent, so any alpha less than in space, but this constant, we cannot make it uniform in time, it's only integrable. In some sense, you could say at the spatial regularity, we're Onsager criticality, but well, it should be independent of time. It is the only that we can do is to have it in N1, so barely. But you could say that our solutions have a Sobolev regularity of having 1/3 of a derivative. And it's funny because if you really look at what it seems to be sharp, it's not a uniform bound, but it seems to be an L3 norm of the constant in time, which is bounded. Okay? Which threshold is actually the correct one in time integrability is not at all correct. It's not. You have 1/3 plus epsilon, and this guy is L3, then you. Okay, so now I lack a what? 5 minutes. Okay, so if I still have a little bit, so since the last actually at least. So if you go back to his embeddings, so you remember I told C1 isometric embedding, C2 are rigid. Okay? Now, C0 solutions of Euler might be C1 solutions of Euler are nice and well behaved. They conserve the energy. Okay? And then the Onsager conjecture tells you there is a threshold alpha in the middle where you should divide between crazy solutions and not so crazy solutions. Okay? So here's the situation for the Euler equations. Of course, you could ask the very natural question, which is, what happens instead of taking in the isometric embedding, I am somewhat in between, so I am alpha. So C1. So of course, it looks like a mere speculation, but in fact, it's a question which was considered in the physics by a Russian mathematician whose name is Borisov. So let me tell you what is the state of the art in there. So we know that the H principle holds for less than 1/5 for 2-dimensional surfaces. I mean, this number becomes different if you are in higher dimension, but for 2-dimensional surfaces in R3, this is the threshold for the H principle, so for crazy solutions. The rigidity holds if alpha is bigger than 1/2, and we don't have physics to tell us what is the conjecture. So Borisov believed the threshold is 1 over 2. My co-author Laszlo believes the threshold is 1 over 2. Gromov believes the threshold is 1 over 2. I believe the threshold is 1 over 3, but I'm the only one. And I even got Gromov against me. So anyway, in both cases, 1 over 3 has a special meaning and 1 over 2 has a special meaning to symmetric embedding. I mean, they're just not random exponents. I'm not just saying it's 1 over 3 here because it's 1 over 3. So my evidence is a little bit better. Okay, so let me tell you about the blue exponents over here. So this has an history. So Borisov in 2000 proved 1 over 13. In a paper with Sergio Conti in 2007, we proved 1 over 7. Actually, this was announced by Borisov in 1963. But when he gave the proof, he gave 1 over 13. And in a very recent paper with a student of mine, Dominic Hinauen, we actually got this 1 over 5. Okay, so what about the upper exponent? Okay, of course, the Euler case was conjectured by Onsager in 1949, and it was proved by Konstantin A. and Titi in 1993. A actually had a slightly weaker. So Borisov in 1958, 2 over 3. Not the optimal one, which we don't know. Now, actually, in 2012, we gave a new proof of 2 over 3. So new meant actually the following. Borisov proves 4 papers, and our proof is 2 or 3 pages. Maybe it's 3 pages, actually. But one important thing is that we have borrowed actually the same idea of this proof of the Onsager, which is an elementary estimate on terms of this type. So it's an idea which we borrowed from Konstantin A. and Titi. Some tricks we essentially can and just not this month, but in January. So a of Uslang actually improved our result, our proof. But I mean, it was not only an improvement, new idea. She settled also another conjecture of Gromov, the exponent to this 1 over 2. Okay, so this is one funny coincidence. Another funny coincidence is the following. So if you look at the constructions, right? So there are all these waves, right? So now the waves which we are piling up in the Euler, they scale like a double exponential. The waves, they scale like an exponential. Now, it's true that only nearest neighbor interactions are in the Onsager conjecture, but if you want to reach 1 over 3, A over here has to be arbitrary. And I mean, when this A is arbitrarily close to 1, this means that actually this double exponential, almost an exponential. So if you want to prove the Onsager conjecture, you have to get almost exponential. You can compute the Kolmogorov spectrum. So this is here. So if you want to reach the 1 over 3 and you compute the kinetic energy of our solutions, you have to reach the Kolmogorov spectrum in the kinetic energy that our solutions have. If you don't reach the Kolmogorov's 5 over 3 law, then our going to give you a 1 over the Onsager conjecture. So there is a link which is from the way we prove things. And one important point is that, in fact, the Euler waves are called perturbed dummy flow, and we that turbulent solutions of that fully developed turbulence fluid dynamics as having solutions which have a piled layers of Beltrami flows in an older idea of the physics literature, although we couldn't make quite the connection with what physicists are saying there. Actually, there's a paper in the mathematics by Konstantin and Maida, but it was inspired by a paper in physics by some. And okay, so let me actually end up with why we're still working on this. So what cannot be done? Well, first of all, we cannot really prove the Onsager's conjecture yet. If you really want to do something which looks to the theory of turbulence, you should also address at least 2 issues. So our construction is very specific, and the theory of turbulence should tell you that there are such solutions. But more importantly, and that is of course very velocity insight. And okay, so we're here's this time. So if you put viscosity, you should see a direction of time in your. Perhaps noticed in my which I told you to observe the kinetic energy. Of course, we can make solutions which dissipate the kinetic energy, But the Euler equations are time reversible. So anytime you produce a kinetic energy, you make a change and you produce a solution of kinetic energy. If you're thinking that viscosity, then of course the other direction shouldn't be allowed to go down. And we don't have an idea how the actually enters into this consideration. So, thank you very much for the attention.